with the Faculty of Engineering, University of Genoa. His main research interests are in the area of humanoid robots, automatic control system and control architecture for robotics and mechatronic system. So, Giorgio, we are interested to learn from you today. Stage over to you.
Thank you very much, Mosen, and it's a pleasure to be here today. What I'd like to talk to you is a dual role of tactile sensing. So robots can touch things and people can touch robots. And so I will give you two views, two kind of experiments that try to address these issues and try to find out how to tackle these aspects. So over the years, there has been a growing interest in tactile sensing. The motivations come from various directions. As we saw before, fine manipulation can be useful in arts, music, and so on. We can exploit whole body interaction to perform complex interaction tasks. The skin has a role in social interaction, so the touching people, and it's a way of conveying information. And of course, and this might be seen as a short-term target, robots are confined, so giving the possibility of having effective human-robot interaction might have a role also, of course, in production. Tactile sensing means having the availability of tactile sensors. Over the years, there has been a large number of demonstrators, mostly at workbench level. And the real difficulty, in my personal experience, is that building effective tactile sensors, which could be ported on different robots, is an activity which involves a lot of work.
Giorgio, I think we cannot see your slide. Can you please reshare it?
Yes, is it shared now?
Yes, now we can see that. I thought it's a problem from my PC, but I think, yeah, now we have it.
Okay, I'm sorry for that. So let me say that we moved over 30 years for very primitive demonstrator. We are now moving slowly to more sophisticated implementation. And the thing is that there's really a lot issues that must be tackled if you want to implement a complete tactile-based solution. We arrived over the year to the development of a technology which is based on capacitive transducers. This is called skin. And as Catherine said, I cannot claim this is the best. It is just one of the possible implementations. So it's a pretty agile way of sensorizing different types of robots. We have implemented this covering of a shunt robot with over 10,000 taxes. I don't know if it's the most complex implementation, but it has been quite a challenge. And we also use the same technology to sensorize a Baxter arm. And again, the number of tactile elements is pretty large. And using the same solutions, we have implemented different gadgets. Force sensor in a day is a 2-axis force sensors that have been truly built in a few hours. We have used this technology to sensorize things, so not just for a robotic application, and exactly the same hardware has been used to develop sensorized fingertips. This is not enough because using the same ecosystem, we could develop Other types of tactile sensors, in this case, this was a fingertip. It's a sort of 16 taxels matrix, sensor matrix that we used, and we are still using to recognize and classify textiles. So, first step of the talk is related to talk about robots touching. The test case that I'd like to introduce is the problem of moving a robot arm in a presence of obstacles, in presence of unknown obstacles, and without using any of the, let's say, state-of-the-art sensors that are typically used for this kind of application. So we assume that no vision is available. We assume that no model of the environment is available. And what we wanted to show was that actually exploiting tactile feedback is a way for approaching this type of problem. You can think of this task as touching or finding some objects beneath a table, so where you can reach the workspace just using tactile exploration. Okay, let me skip maybe the details. We approach the problem as a priority-based control scheme with two goals. One is the final reaching position. The other one is the problem of controlling the forces. The scheme that we get is a cascade loop with a force and a position loop, nested loops, and these are some results, some experimental results. This is the playground. We have 5 obstacles and 5 target points. And during the process of reaching the target point, starting from different initial conditions, you can be in subject to different type of constraints, single contacts, multiple contacts on the same link, which makes the usage, for instance, of sensorized joints not so effective, and of course, multiple unpredictable contacts on different parts of the robot. The problem is complex, so we cannot pretend to have an analytical result, but by the statistics that we got are that the method works, and works pretty well, because with a few exceptions, the task has been completed. This is a short view of the kind of events that happen during the motion. We have a quasi-exponential convergence of the position to the goal, with multiple contacts arising during the operation. And this is the result. Problems. Okay, this is a sequence of operations, and you can see how the robot moves. In this case, you will see 2 different results starting from different positions. The point C is reached with different strategies, and you can see on the right hand side that the motion is pretty natural. Okay, and of course the things are not always going well. This is a case where the robot gets stuck in a local minimum, despite the fact of attempting. In this case, it gets locked by multiple contacts. Okay, so just a few remarks. What you have seen is, on one side, one way of exploiting tactile sensing to perform an autonomous task in a very non-structured condition. And of course, what we got is a sort of best effort strategy. There are ideas to go beyond that, and one of them is to adopt a SLAM-like tactile-based exploration strategy in order to enhance the robustness. There is a difference, of course, between tactile sensing and vision, although we will see later that we can exploit some ideas coming from vision to process tactile data. And there are other ideas that in part will be explained in a paper later today by Alessandro Albini that will show you how the tactile data coming from complex geometry like the one characterizing the shape of a robot could be addressed for this type of operation. So now we can move to the second side of the problem, which is touching robots. A few years ago, we started working with the idea of using or exploiting tactile sensors, large area tactile sensor, to allow person to give a command. This might be used for teach by demonstration tasks or whatsoever. So we invented a sort of language, of touching language. So in this sense, it is pretty natural to design a controller for this type of operation. But then we realized that one particular issue which might be relevant is to understand whether a contact is a purposive contact, is a contact given by a person, or is an accident, or is a contact with the environment. So we started addressing a very specific and important issue, which is to recognize human touch and trying to classify it. Now the question is how to proceed with the processing. The ideas that we explored is somewhat motivated by how the tactile data are mapped onto the cortex of the brain. So we have a sort of transformation from 3D to 2D. So what we do is to transform the 3D representation of the tactile data into a 2D representation, and then by transferring back the process information into 3D. So what we do is basically the following. We get a pressure map due to the contact. The contact is then transformed into a 2D, let me say, standard image. And then we proceed at this level with recognition to discriminate between human contacts, hand contacts, and non-human contacts. And once we recognize that the touch is given by a person, we arrive to segment the various parts of the hand, and in case to back project them onto the 3D space. We do this by using convolutional neural network. In sequence, the first step is to perform a classification, and after that, a semantic classification. This is what happens in a very special case, and what we designed a specific convolutional neural network that led to pretty satisfactory result, both for classification and for segmentation. What is interesting is that we analyzed the robustness of this method and the robustness of the solution that we proposed in presence of failures. For instance, okay, the robot skin is something which is prone to break. So we assume to have a degradation of the performance of the skin over the time. And what we found is that the method based on the convolutional neural networks, it's pretty robust in presence of patch failures. As you can see here, the red spots represent patch failures, or in the case of degradation in the response of the tactile elements. By the way, this analysis on the degradation of the tactile elements is also an interesting hint for the design of tactile sensors, since it gives a sort of idea of how many tactile elements might be required for a given type of application. And the last step that we did was related to the possibility of porting the machine, the neural networks, on different type of geometries. And we exploited this portability issue to a practical case where we are involved. Collaborate is an European project where the task where we are involved is the problem of human-robot collaborative task. We have a very big, heavy-duty robot which supports a windshield, and the human operator is expected to perform some inspection and assembly operation on the windshield. So in this case, the idea of using tactile sensors was motivated by the possibility of enabling a tactile-driven control of the motions of the arm if the system recognized that the touch is a purposive one. So it enters fully within the ideas that I explained before. This is the prototype of the collaborated handles that we have developed. And this is today what's going on. We are proceeding with the integration of the hardware on the gripper. We expect to make the experiment, start to make the experiment in the next few weeks. And these are some desktop results. As you can see, under different conditions, we are able to recognize the contact with the end. And as you will see, there is also the possibility of recognizing multiple hands, multiple contacts with the ends, and to discriminate between purposive and non-purposive types of commands. And of course, this is another example of possible interaction, types of interaction that might arise. This is the example of the segmentation with respect to the recognition that we could implement on an embedded computer installed on the gripper. In this case, we need to use a quite powerful machine. So this is not implemented using, at the current stage, it's not implemented using an embedded computer. But as you can see, there is a pretty good capability of segmenting and recognize also multiple hands. By the way, in this example, we perform a frame-by-frame processing. We have not yet implemented any time filter, so there is no temporal filtering. So every tactile frame is processed in sequence. The very last bit, time is almost over. There was a third chapter in this discussion, which is robots touching robots. We have made experiments over the years on self-calibration of robots. I haven't mentioned calibrating tactile skin is sometimes not an easy task. You have to repeat it from time to time, and this is because we are working with tailor-made solutions, so there are no yet industry-grade solutions portable for different robots. And while I was thinking of this, I reminded this video. This came from a project where I was involved. I was the coordinator of this project, RoboSkin, about 10 years ago. And I recall this video where a robot is punching, is hitting another robot. So it's a sort of interesting scenario of robots interacting in tactile fashion with other robots. I can't imagine at this stage which might be the purpose, but it's a quite funny idea. So I think I remained in the right time. Let me just thank the people that was involved in this presentation, that who gave contribution over the year to the development of the technologies that you have. So
excellent. Excellent. Thank you very much, Giorgio. Very interesting. Is there any question here? Yeah, please, Luca.
Yes. Hi. Thank you for the interesting talk. I have a question regarding the hand classification.
Yes.
Did you train this yourself? And if not, how does it generalize across different hands?
Okay, this is, let me move back. Yes, this is the recognition at this level was made using 90 subjects. So the number of people involved was quite large. As you can imagine, this is a tedious part. And we exploited the fact that we could use this trained network as a starting point for the second implementation, the handle implementation. In this case, we started from the originally trained machine, and we performed just a fine-tuning on the classifier side of the network. So basically, in this case, the convolutional layers basically remain the same as in the original network that I showed you.
Okay, thank you.
Thank you very much. Is there any question here?